So, we are discussing about the specific heat of solid. So, at high temperature, it is nicely explained by Dulong-Petit law as well as by Einstein theory, but problem is to explain the lower temperature behavior of CV, specific heat. So, actually experimentally it is found that that CV is basically proportional to T cube, but in case of Einstein theory that we have seen that in case of Einstein theory, we have seen that CV at low temperature it is proportional to so is exponentially dependent. 1 by T square term is there, but it at low temperature towards 0. So, these exponential terms dominate, right. So, then Debye came forward to explain the low temperature behavior of specific heat. So, that is we tell this Debye theory. So, in case of Dulong-Petit law, there these atoms in a crystal that was considered as a like gas particle. So, it can take energy from 0 to infinity, and then that way it was treated and got the result, which is only explain the high temperature behavior of specific heat. Then Einstein, what he assumed? Einstein assumed that that atoms in crystal, it is not behaving like gas particle. It's situated at the lattice point, or lattice point itself is itself can vibrate. So, as if in each lattice point our atoms are there. So, in this case Einstein considered that each lattice point or atoms vibrate with respect to its equilibrium position, but so each vibrate and they vibrate independently. They vibrate with same frequency like harmonic oscillator, they vibrate with same frequency, say nu, as if this harmonic oscillator is oscillating, vibrating, and so there. So, lattice points or atoms in the solid, they are independent. So, they independently oscillate. So, that was the assumption of Einstein, and he calculated the total energy of the system, and from that he found the CV, which depends on exponential term at very low temperature. So, then Debye realized that no, this is not the correct assumption. because lattice points are not, they cannot oscillate independently. They are coupled with each other. So, like as if they are coupled with each other. Okay. So, like mass spring system. Okay. So, they oscillate or vibrate as a whole, the lattice as a whole they vibrate or they oscillate. Okay. So, that was the assumption of Debye, and they do not vibrate with just one frequency, they may vibrate with many frequencies. So, each vibration as a whole, each vibration is expressed in terms of mode of vibration. So, each mode will have frequency. So, for different mode, so mode are differentiated with in terms of the their frequency. So, different mode will have different frequency. Okay. So, further he assumed that this basically elastic, this vibration of the lattice, it will generate elastic wave, or when elastic wave will propagate through the lattice, through the crystal. So, this lattice as a whole, it will vibrate. So, it is vice versa basically. So, he assumed that this wavelength of elastic waves generally it is higher than the lattice constant or distance between two lattice points, that is very small compared to the wavelength of the elastic wave. Okay. So, when elastic wave will propagate through this crystal, so it will see this crystal as a continuum medium. It will not see the discreteness of the lattice points or atoms in the crystal. So, he assumed that this elastic wave will see the system as a continuum system. So, instead of this discrete array of lattice points, he considered that this, in case of elastic wave, it is a continuous medium. So, a one dimensional lattice array we can replace with a string. So, he considered basically string, a wire under tension, the string. Okay. Now, the strings, so string whatever crystal as a whole, this crystal is vibrating, that so one dimensional crystal is vibrating as a whole. So, that is considered as if the string is vibrating. Okay. So, I think you are quite familiar with the string vibration. Then it can express in terms of wave equation, right. So, this say 0 and this length of this string is L. So, at a point x, if you disturb it by ux as a function of u as a function of t, that is the just displacement, say this is the just displacement of the string, disturbance of the string at point x. Okay. So, this disturbance, this is u x t. Okay. So, u as a function of x. So, disturbance we express at any points on the string and at any time t. Okay. So, if u is the disturbance of the string, so one can set differential equation or wave equation for string vibration. So, that is well known wave equation, that is valid. This equation is valid for any wave. It can be electromagnetic wave, it can be sound wave. So, sound wave is basically elastic wave. So, d2u, this function of x t, so dt square, sorry, dx square equal to 1 by v square d2 u dxt by d2 dt square. Okay. So, this is the wave equation. So, v is the velocity of wave, velocity of wave through the string, So, v generally square root of y by rho. So, y is the Young modulus of this medium and rho is the density. So, in case of string, so mass per unit length, in case of 3 dimensional material, so this the mass per unit volume, it is taken mass per unit volume. Okay. So, this is the wave equation. Now, if the string is fixed at one end, then if it just vibrate, so then you will get this basically travelling wave. The solution will be basically can be the travelling wave, but when these both end are fixed, then this wave will be confined between these two ends. So, basically this wave will reflect from this other side. So, when come back here, so it is reflected. So, they will form standing wave, okay, or stationary wave. So, thus this for this equation, wave equation, so under our boundary condition, so the solution will be stationary or standing wave. So, the solution, standing wave solution, this x is a function of t. So, this I am writing un equal to a sin k n x cos omega n t. Okay. So, n is basically mode of vibration, n is basically mode of vibration. Okay. So, this it will vibrate with different mode. So, that mode is designated by n equal to 1, 2, 3 etcetera, that we will see later on. So, where where this kn is basically 2 pi by lambda n, lambda n is the wavelength of nth mode, and omega n is equal to 2 pi nu n, n is frequency and omega n is the angular frequency of nth mode. So, this solution has to satisfy this boundary condition, because at x equal to L, this all the time this displacement has to be 0, means u n for nth mode x equal to L and at any time t, okay, this has to be 0. Okay. So, when it will be 0, this cos omega n t for any time it cannot be 0, okay, a cannot be 0, then all the time it will be 0. So, only this part has to be 0, sin k n x has to be 0. Okay. So, sin this condition is telling sin k n x has to be 0, okay, when x equal to L, when x equal to L. So, this has to be 0. So, obviously, from here k n, okay. So, k n L it has to be n pi, it has to be n pi, sin n pi is 0, n equal to n equal to 0, n equal to 1, n equal to 2, etc. But later on I will show you that n cannot be 0, it has to be greater than equal to 1. So, that we will see. So, condition, this boundary condition is giving us that k n L has to be equal to n pi. Okay. So, this k n is 2 pi by lambda n, k n is 2 pi by lambda n into L equal to n pi. So, from here you are getting lambda n equal to lambda n. So, pi will go. So, lambda n will be equal to 2 L by n, it will be 2 L by n, right. So, here if n equal to 0, then lambda n is infinity, right. So, that is not allowed, lambda has to be within this length. Okay. No, it is not correct, it is not correct. So, here, so is lambda n will be infinity. Okay. So, that has no meaning. So, that thus we avoid this n equal to 0. So, we consider that n will be greater than equal to 1. Okay. So, then we will see that this omega n equal to 2 pi nu n. So, basically nu n equal to velocity by wavelength, this lambda n, right. So, this velocity by wavelength. So, lambda n equal to 2L by n. So, 2L by n. So, it will be n v by 2L. Okay. So, basically here you can see this wavelength n equal to 1, wavelength lambda 1 it is 2L, and nu 1 it will be v by 2L. Okay. So, for first mode lambda 1 nu 1, for second mode n equal to 2 it is lambda 2 will be L, and nu n means nu 2 will be 2 v by 2L, means v by L. Okay. So, we will get different mode of vibration having different frequency and wavelength also. Okay. So, here this length is fixed as well as this velocity is constant, because it depends on, as I showed, that Young modulus of the material and the density of this material. Okay. So, v is fixed, okay. V is constant. So, velocity of waves in the string is constant. So, ultimately what we are getting, so I think I will leave it. the solution we are getting un function of x t equal to a sin n pi by this k n. What is the k n value? K n value is 2 pi by lambda n is 2l n. So, n pi by l, right, n pi by l cos 2 pi nu n t, and here I have to put x. Okay. So, this is the for one dimensional case, this is the wave function for nth mode. So, from here you can see basically in this case you will get frequency as a function of frequency, you will get equidistant frequency for defined mode. So, one can find out density of modes z nu, density of modes. Okay. So, one can find out. So, that is basically dn by d nu, density of states, it is basically dn by number of modes within the range of frequency d nu. Okay. Okay. So, if you get density of states at different frequencies, and for each frequency what is the average energy of the mode, okay, then you will get the energy for that mode, okay, and then you can integrate for all modes. Okay. So, let us do it for 3 dimension, because our system is lattice, that crystal is 3 dimensional object. Okay. So, this wave function whatever we got, so that can be this for 1 dimension, that can be extended for 3 dimension, So, like then you say you can write n or x. So, n I will avoid now. So, u as a function of x, y, z, t. So, in 3 dimension. So, this solution will be standing wave, and this one can write a sin n pi x by l. So, this I am putting index x, n x for along the x axis, then sin n y pi y by l, then sin n z pi z by l, and then your cos 2 pi nu t. Okay. So, that will be the solution for 3 dimension. And if you, so this solution for which wave equation, the 3 dimension wave equation, that is basically d to u as a function of this x y z t, d to u by d x square plus d to u by d z dy square plus d2u by dz square equal to 1 by v square d2u by dt square. So, that is the wave equation for 3 dimension and corresponding solution is this. Okay. So, now if you put this solution here, it has to satisfy this equation, then only it will be our solution. So, here we have considered that this material is this crystal, this solid we have taken as a cube, So, each side length is L, and there the face of the cubes are fixed. Okay. For one dimensional string, so both ends are fixed. So, under that condition we got this solution. Similarly, similar solution we have considered for 3 dimension. So, condition has to be similar. So, here this this all faces of the cube are fixed. Okay. So, under that condition this will be the solution and this has to satisfy this equation. So, if you put here, so what you will get? So, nx pi L square you will get, twice differentiation you have to do. So, basically you will get nx square pi square L square, ny square pi square L square, right, equal to. So, here you will get nx square, take common, pi square by L square plus ny square plus nz square equal to other side 1 by v square, twice differentiation if you do 2 means 4 pi square nu square here. Okay. So, if I take this pi square by L square this side, so it will be L square by pi square, right, it will be L square by pi square. So, pi square will go. So, ultimately you will get 4 L square nu square by v square. Okay. So, basically what you are getting? You are getting nx square plus ny square plus nz square equal to this. Here L is constant for your cube. For a particular mode nu is fixed, and velocity is constant, okay, in this medium. So, basically for a particular mode, so this square of this nx square plus ny square plus nz square equal to constant for a particular mode of having frequency nu. Okay. So, for different nu, basically for different nu value, for means for different mode, you will get different sets of value of nx, ny and nz. So, basically nx, ny, nz is set value of a set of this will represent a mode under this constant, So, this I can write as a r square. Okay. So, in this nx, ny, nz axis, nx, ny, nz axis system. So, you will get a basically sphere of radius r, you will get a sphere of radius r. Okay. So, this radius So, R for a particular frequency. So, R for a particular frequency R. Okay. So, between R plus dr, so we will get those mode in the range of nu to nu plus d nu plus d nu. Okay. So, in this frequency range we will get number of modes, within this spherical shell of radius, this is r and this radius is r plus dr. Okay. So, this sphere and with the thickness of the sphere, spherical shell thickness dr. So, here whatever the points, each point will represent a mode having frequency nu to nu plus d nu. Okay. So, how many number of states modes will be there? So, that one can find out. So, what is the volume of this spherical shell of this cell? So, this volume of this cell, I think I do not need this anymore. Okay. So, volume of this shell will be 4 pi r square, that is the surface area of this sphere, and yes, and then volume will be into dr. Okay. So, that will be the volume of this. So, in this volume, so we will get the total number of modes having the frequency between in this range. Okay. So, basically nx, ny, nz, like n is greater than equal to 1. Similarly, nx, ny, nz, is also one has to its value nx, ny, nz, it is also greater than equal to 1. Okay. So, if you see this sphere, it has 8 octet, it has 8 part. So, only one part, one of this 8 part, that will be in the what I should tell, that that will be, that part will have only the positive nx, ny, nz value, right. So, you have axis system, right, x, y, z. So, if you consider sphere, so only this part, so positive nx, positive ny, positive nz. So, only this part will have the positive nx, ny, nz value, right. So, in this half nx will be negative, right. In this half ny will be negative, nx will be negative. In this half ny will be negative, right. So, similarly, if you go below, so all will be negative. So, 7 part will have the negative value, 1 or both or 3 will have negative value, only all will have positive value in this part. So, that is why the states will get, number of total states will get this 1/8 of this one. Okay. So, in the frequency range of nu to nu plus d nu. So, here what we have got, so I have to, so this r basically is related with the nu. So, r square, what we have taken, r square equal to 4 L square nu square by V square. So, between R to R plus dr. So, that corresponds to between nu to nu plus d nu, right. So, differentiate it R dr equal to 4 L square by nu square V square nu d nu, okay, nu d nu. So, from here you can find out dr equal to 4 L square V square and divide by 1 by R. So, R is basically 2 pi nu by V. So, 1 by R it will be V 2 L nu, okay, and then your nu d nu is there. So, this nu will go. So, here I will get 4 that was 1 by R. So, R is this 2 pi nu into V, okay. So, here we will get this V, this square will go, this L, this square will go, this 2, it will give 2. So, I will get 2 L by V, 2 L by V d nu, 2 L by V d nu, okay. So, this is representing basically density of states as a function of, okay. So, let me, so this will be equal to pi by 2, R square is that one, 4 L square nu square by V square, okay, and here is I found 2 L by V d nu, okay. So, from here you are getting what you are getting, this 2 will go, I will get 4 pi L cube, 4 pi L cube then I am getting by V cube, velocity cube nu square d nu, okay. So, this basically density of states Z nu d nu in the range of frequency d nu from nu to nu plus d nu, in that range total number of mode in that total number of mode in this volume will be this where this frequency range varies from nu to nu plus d nu. So, that will be the total mode between these two frequency range. So, if we express this Z is a density of modes. So, then within this range what will be the total number of modes. So, that one can write this, okay, one can write this. So, I think here, so I will stop here and then I will continue the calculation in next class. So, thank you for your attention.